Okay. Hi, everyone. Welcome to another Origin Seminars. And today we have two speakers. And our first speaker would be Avery. Avery has been a postdoc with us for 2 years already. And I hope everyone has already had some interactions with Avery in the past and also know each other. But if you haven't, make sure to say hello after this and to have some chats with Avery. So Avery got his PhD in the Princeton University, and later Avery did a postdoc at University of Nevada. And he did many research, mostly focusing on the formation and evolution of the planets in the protoplanetary disks, and mostly on theoretical modelings and applications on the own solar systems, such as the jet planet formation. And today, Avery is going to talk about his recent work on the radiating Bondi flows. And Avery, the floor is yours.
Thank you for the introduction. Hello, everyone. I'm Avery, and today I'll be talking about some work radiating body flows. Some of you may have seen this before, and I apologize if you have, but I've included some sort of updated stuff that will hopefully keep you interested. This is work that was also done in conjunction with Andrew Uden at Caitlin Crider here at the university, and is published or submitted to the journals under a series of 2 articles, and is currently on the archive for you to peruse. So to get started, let's start with the basics. So what is a giant planet? In our own solar system, we can kind of divide the giant planets into 2 categories, one being the gas giants, so Jupiter and Saturn. These planets are more massive. They have lots more hydrogen and helium. And outside of our own solar system, we have other examples of this, like hot Jupiters. The other category of giant planets within our solar system is the ice giants. So these are lower mass, and they contain more rocks and ices, analogous planets around other solar systems would be sub-Neptunes in the exoplanet context. And so how do we form these giant planets? Well, the leading hypothesis for giant planet formation, I would say, is core accretion. And so to give you a brief overview of this process, we begin with the smallest things in the protoplanetary disk, essentially dust grains, that will coagulate and grow to form planetesimals through a mechanism like the streaming stability. Once we have these kilometer-sized planetesimals, they will collide and accrete other solid material to form protoplanetary cores and protoplanetary embryos. Once they reach a significant enough mass, they begin to accrete gas from their surrounding protoplanetary disk. And while all this is going on, they also experience sculpting effects like planet migration and planet-to-planet scattering. In this talk, I'll be particularly focusing on the accretion of gas, which we can subdivide into sort of 2 stages in this core accretion picture. In the first stage, there is a very long process of Kelvin-Helmholtz contraction. In the early sort of formation process, the mass of the envelope of this giant planet is less than the mass of the core of the same planet. And so the way that this envelope grows is by cooling and contraction. And this happens sort of quasi-hydrostatically, and it takes about 1 million years, give or take. Eventually, the mass of the envelope becomes enough to exceed the mass of the core, and then we enter the stage of rapid cooling and hydrodynamic runaway accretion. In this stage, the accretion is somewhat Bondi-like. You just have material sort of free-falling onto your planet, and producing an accretion shock where it hits the planetary surface. And this phase of runaway accretion is the predominant phase that I'll be concerned with today. And so we can hope to look for some signature of this theoretical picture in the observations. This idea of a slow, protracted, low mass cooling phase followed by a rapid runaway phase would seem to suggest that the planets we observe should fall into sort of a bimodal distribution. Either those planets that grew mass enough to hit this runaway phase and grow all the way to gas giants, or planets that did not manage to hit this runaway phase and became stuck as sort of ice giants. And so here we're showing the FGK occurrence rates of planets from Kunamoto and Matthews. And I've drawn sort of indicators for the radius between the gas giants and the ice giants. And while we do see some evidence of a bimodal distribution at very short periods, so like 1 day, this sort of bimodal binary distribution does not become evidently obvious at longer periods of 100 days. There's potentially some signature in microlensing data, but it's nowhere near as binary as one might think, just from this simple core accretion picture. Which raises the question, are our runaway accretion rates too high? And are we essentially underpopulating this exoplanetary desert between ice giants and gas giants? So in particular, let's think about what people do when they produce sort of demographic expectations for these theoretical models. Here I'm showing the flowchart from the Bern models of population synthesis works. There's all sorts of ingredients that go into these complex models to build synthetic populations of exoplanets. But I'd like to focus on the gas accretion, in particular, these three blocks. And so the maximum accretion rate that sets the growth of this planet in the runaway regime is fundamentally a function of the planet mass. And this is because the Bondi rate itself depends on planet mass. But we see in these models that it's really only dependent on the planet mass. It's also dependent on some other quantities like the surface density through the protoplanetary disk. But there is no sort of feedback between what is happening energetically in the envelope and the accretion flow itself. In particular, the energetics are potentially oversimplified. They assume some sort of classical Bondi adiabatic equation of state. And so we might wonder how might luminosity or other radiative effects affect this actual accretion rate of the gas. So to start with sort of the simplest thing that people do, they invoke some sort of Bondi-like 1952 accretion scenario for treating this accretion process. In 1952, Bondi established sort of the spherically symmetric steady state accretion solution, shown here on the right. And so what he did is he found there are these different classes of solutions, and the one that is essentially an accretion solution is shown in yellow. And so it's the Mach number being plotted here as a function of radius. You can see that the flow begins at large radius as the subsonic, nearly hydrostatic flow. But then as you move inwards closer to the planet, the flow speeds up and it passes through this critical sonic point, marked here with, I guess, a B or a B prime. Past the sonic point, the flow becomes supersonic, and eventually this flow will hit the planetary surface and shock and produce its own luminosity. The fundamental result of this work by Bondi was that this mass accretion rate really only depends on a single parameter, gamma, the ratio of specific heats. And so we can write our Bondi accretion rate as just something being the function of planet mass and then also quantities of the surrounding environment, so the density and infinity and the sound speed and infinity. And so this is what people sort of use in one way or another in planet population synthesis models. Let's think about how we could extend this to include feedback and radiation from this very hot accreting planet. Now, instead of treating this as sort of an adiabatic equation of state, with the entropy being constant, we're saying, let us allow the entropy to be changed by the luminosity that is released during the accretion process. And so you'll see I have the entropy profile being tied directly to the luminosity profile. In including this radiative feedback, we introduce now 3 other dimensionless parameters to the problem, all of which are sort of quantities related to the radiative properties of this flow. And so you have the optical depth, specifically the optical depth through the Bondi radius. You have some characteristic luminosity of this accretion, and then you also have a characteristic cooling time. And so fundamentally, what we're going to ask is, what is the mass accretion rate once you include this radiative feedback? And we're going to parameterize it in terms of this F factor, or a correction, to the adiabatic Bondi rate. So if F is 1, that means that the adiabatic Bondi rate is totally sufficient in this treatment. But as we'll see, it ends up being that F accretion can be significantly less than 1, meaning that accretion is suppressed relative to the adiabatic rate. So to begin, I'll show you some example solutions from our paper 1. In particular, we've made the assumption here of the flow being optically thin, and also having very fast cooling. And so similar to the transonic Bondi accretion solutions where you have flow starting at subsonic speeds and then transitioning to supersonic speeds, I'm showing Mach number profiles on the right of these different radiative solutions. So again, the Mach number profiles begin subsonically and then they increase to some supersonic transition point. What we see though is as we crank up the luminosity, what's actually happening is the flow is being heated near the sonic point. The sonic point itself will adjust to where GM over R is about equal to K times T. And what this does is it pushes the entire Mach number profile inwards. It pushes the sonic point inwards, essentially. And what this means is that higher luminosity essentially is giving us a smaller effective Bondi radius. For each of these different luminosity curves, I've also plotted the F accretion factor or the accretion rate in the bottom panel as a function of the luminosity. And we can see as we crank luminosity higher and higher, this F accretion sort of tanks, and we get a much lower accretion efficiency than what would otherwise be determined from just adiabatic Bondi accretion. So that's all well and good, but we can do this for sort of all of these parameters in general, all these radiative parameters. We have the optical depth, the luminosity, and the cooling time. So we've gone ahead and done this, and we've mapped this out as a function of these three parameters. Here I'm showing just a slice of what happens as you change the optical depth, or you change the luminosity at fixed cooling time. And the kind of main result of this is that radiative feedback tends to suppress accretion. We see through much of this parameter space of optical depth and luminosity, F accretion tends to be lower than 1 and can be very significantly low. In particular, we see that it is suppressed as we go to high optical depth in this plot, or high luminosity, and then also long cooling times. So this is sort of the fundamental result of our first paper. Is this general scaling of accretion feedback or radiative feedback with different radiative parameters. So now we can hope to apply this to sort of planet forming conditions, which is the motivation for our paper 2. I've just shown that the accretion rate depends on these three-dimensionless parameters. But in a more realistic sense, we can expand these parameters into actual planet parameters, such as planet mass, the local disk temperature, the local disk background density, the opacity. And so that's what we're more concerned with in this second paper, is how does F accretion, or the accretion efficiency, depend on properties of the planet, like planet mass, disk temperature, etc. So we've constructed sort of a fiducial protoplanetary disk with these particular power laws here. And then at each point in the protoplanetary disk, we've placed a protoplanet of mass m. And we've asked for this given protoplanet of mass m, and at this radial location in the disk, what is the radiating steady state that we get from solving these Bondi equations? So that's what I plotted over here on the right, is what is this Bondi accretion rate as a function of formation location on the x-axis, and then planet mass in Earth masses on the y-axis. And so at large sort of outer disk regimes greater than 10 to 30 AU, we find that F accretion is about 1. And so that tells you that the adiabatic Bondi rate is sort of totally sufficient to describe this type of accretion. However, in the inner disk, we find sort of substantially suppressed accretion rates varying from 1 to 2 orders of magnitude, interior to 10 AU. So there, adiabatic Bondi accretion is not an accurate descriptor of this process and requires some sort of inclusion of this radiative feedback effect if you hope to model sort of this accretion process appropriately. We can ask, why is this happening? What is driving this accretion suppression in the inner disk? And we find that it's mainly a function of the inner disk being very dense and very optically thick. So over here on the right, I'm showing the fiducial depth through the Bondi radius, the optical depth of the Bondi radius for these different models. And we can see that the radiative parameters whole sort of protoplanetary disk depend a lot on your formation location. So in the outer disk, 100 AU, things are very optically thin. The optical depth is like 10 to the minus 3. Whereas in the inner disk, say like 1 AU, the optical depth is almost 6 orders of magnitude higher in this particular disk model. And as I said earlier, radiative feedback suppresses accretion, particularly at high optical depth. And so in the inner disk, where you have some orders of magnitude higher optical depths and higher surface densities in the protoplanetary disk, the planet experiences much greater radiative suppression. And so the takeaway point of sort of our paper 2 is that accretion suppression in the inner disk is driven by increased density and the corresponding increased optical depth there. Since I say this is very dependent on optical depth and surface density, we should also consider sculpting mechanisms that could change any sort of surface density you think of. And so the thing that immediately comes to mind is, oh, what if this planet opens a gap? If this planet opens a gap, it'll lower the surface density, lower the corresponding optical depth, and it may push you back towards a sort of adiabatic-like accretion regime. In particular, I've shown over on the right, what is the expected optical depth for including gaps in these models based on the planet's mass and semi-major axis. I've made some assumptions about viscosity here. I think alpha is 10 to the minus 3. But you can see that in the inner disk, when planets open gaps, they reduce their local surface density by factors of, say, 100, 10 to 100. So we could expect the radiative accretion rate to be very different in that case. So what we've done is we've gone ahead and we've repeated the analysis that I just showed. We've included some sort of parameterization of these planet-carved gaps. So assuming every planet opens a gap at this particular gap depth on the right, we find sort of similar results for the outer disk. Things are still optically thin. Even if you open a gap, you're just changing things from optically thin to optically thin. However, in the inner disk, where planets can open fairly deep gaps, and they were previously optically thick, the lower surface density now makes these things more marginally optically thick. So while we still get sort of accretion suppression rates of 10, they don't go, there is no accretion suppression of 2 orders of magnitude. So this is sort of a order of magnitude effect once you include gap opening. One can also ask, okay, we have this sort of scenario where every planet opens a gap, but under what conditions should various planets actually open gaps? And so if we consider sort of gap opening timescales, we can estimate where we expect planets to open gaps, and we should use these rates I just showed versus the earlier very suppressed rates. And so what we find in particular is that gap opening tends to operate fairly generically in the inner disk. The gap opening timescale tends to be very rapid, and so this is shorter than the accretion or the viscous timescale. And we end up with planets in the inner disk opening gaps fairly robustly. In the outer disk, planets have a lot of trouble opening gaps, particularly because viscous processes operate to close these gaps. But in the outer disk, it doesn't really matter what you choose about the radiation, because in both cases, it's about 1. So that's kind of our fundamental result, is that in the outer disk, adiabatic Bondi accretion rates are fine, but in the inner disk, the accretion can be suppressed by 1 to 2 orders of magnitude, specifically 1 order of magnitude if those planets open gaps. I will end with just 2 short sort of things that I would like to emphasize. One, we put a lot of work in this project into developing open source tools. Our goal is for people to use these radiative accretion rates in their accretion models. And so we posted to this GitHub sort of 2 simple Python functions that, given a set of planet parameters like mass, protoplanetary disk density, temperature, opacity, it will just spit out what this F accretion factor is. You can then multiply whatever accretion rate you already have by this accretion and get sort of an appropriate radiative Bondi rate. It will also compute the luminosity for you if you use this other function. But in particular, this is a set of analytic and tabulated solutions for like fast retrieval and incorporation into existing models. We also include some nice sort of examples and walkthroughs about how to use these particular functions. The other quick thing I'd like to mention is just that we are currently sort of extending this work to look at what happens in 2 dimensions. So in 1D, all the stuff I've mentioned is sort of 1D spherically symmetric. You can't have any sort of rotation involved. So more recently, we've been extending these 1D calculations to 2D, where you have rotation and radiation having interplay to lead to some sort of overall accretion rate. And what's interesting about these sort of preliminary results is that we see sort of along the pole of these 2D simulations, we see something that looks like very much like 1D Bondi accretion. You can see over on the right panel, I've plotted the radial Mach number. So anything that's dark blue here is essentially free falling supersonically onto the planet. This looks very much like a 1D Bondi accretion picture. However, near the midplane, there is no such free fall. In particular, it's because things near the midplane are rotationally supported. They have a significant amount of angular momentum. This allows them to form sort of a circumplanetary disk. You can see a high increase in surface density here. And in particular, the accretion through the midplane is certainly not Bondi-like. So now, sort of Bondi accretion and any radiation involved becomes a very two-dimensional picture, and that the pole is operating sort of 1D, and the midplane is operating very differently. So I'll just end with a short summary of everything I've talked about and sort of key takeaway points. In paper 1, we showed that radiative heating and cooling operates mainly to suppress 1D Bondi accretion, and this occurs at high optical depth, high luminosity, and long cooling times. And then once we apply this to actual sort of planet formation regimes, it appreciably suppresses accretion for planets in the inner disk where density is high. If planets don't open gaps, we should lower these accretion rates by 1 to 2 orders of magnitude. However, they likely do open gaps in the inner disk. So it's sort of most appropriate to lower these accretion rates by a factor of 10. And then finally, we've included these open source tools for people to compute the results of these works to implement in their own sort of accretion models. So thank you, and I'm happy to take any questions on the matter.
Any questions? Well, I have a question. For the open source tools you developed in the Python version, would it be easy to implement those into, for example, Athena++ or other video transfer tools if they want to have those abilities?
I think so. It's a bit trickier with sort of things that aren't written in Python, right? Here I've just given sort of Python functions that are easy to import, etc. But I did give sort of an example in the Jupyter notebook of how you might do this for a code that's not written in Python. That doesn't necessarily involve rewriting all these functions in the language of choice. Essentially, from these Python functions, you can make sort of a lookup table for different masses, temperatures, and stuff. And then you can stick whatever lookup table into an actual code like Athena, which should be fairly straightforward to do. But I've included sort of an example of how one might do this for things that are not just Pythonic. Otherwise, it's just an import Bondi tools and then use the function.
We have an online question. Nick, do you want to ask your question?
Sure. Hi, Avery. It's Nick. So it looked like you had luminosity, which was sort of just a free parameter, but you might imagine L depends on m dot if it's accretion powered, and then m dot depends on L. Can you do like a coupled version of the problem where all the luminosity comes from accretion?
Yeah, so in these like paper 1 solutions, luminosity is indeed a free parameter. However, in moving to the planet case, and producing these plots like these, we no longer take L as a free parameter, and we do calculate sort of the self-consistent L equals GM M dot over R planet. So that is something we've sort of taken into account for these particular planetary applications. Yeah.
Cool. Thanks.
And that's also, I guess, part of the origin of having two functions here, one compute F accretion and one compute luminosity F accretion. So the first function assumes luminosity is a free parameter. The second function does not assume luminosity is a free parameter. It asks for what is the shock efficiency of the radiative shock and what is the location of this particular shock that's producing luminosity. And from that, it will give you sort of a self-consistent accretion luminosity as well as a self-consistent accretion rate.
Nice. Thanks.
You mentioned that the classical models, they model the envelope like a polytropic simple function. Have they tried to model like a piecewise into a polytropic function, like to improve the classical model?
Not through, I guess, not through that like line of enhancement, I guess. Like there are sort of two ways people do this. One is take accretion functions fit to 3D simulations. So that's one way to sort of capture some effects. But as far as the other way, which is just treating it as sort of like a 1D Bondi problem, I don't think there's been any sort of relaxation of the fundamental assumption that P is rooted again. That comes straight from sort of Bondi's original work, and no one has really relaxed that assumption in time since, I would say, at least for these applications. Yeah.
And you apply this for planet formation, but can be applied to star formation?
The reason why it's so nice for planet formation is because they're very cold environments. So I've made an operating assumption in all of this that like radiation is important in heating material, but the pressures here are sort of still cold and gas dominant. There may be some hope of like extending this to hotter star forming regimes. But a lot of the assumptions that I baked into this so far are that things are fairly cold. So just be wary of anything along these lines. And that's particularly why it works well for planets.
Is it always fine to neglect planetesimal accretion luminosity, do you think? Any part of this parameter space where it might matter?
I guess for these like truly maximum accretion rates, I would say doubtful. But I haven't done the actual calculation. But some of these rates, are like some of these maximum accretion rates that are not necessarily very long lasted are like accreting 1 Earth mass of hydrogen in 100 years. And so that I think will dwarf any potential planetesimal accretion. Where these rates are sort of most applicable.
We also have one comment from Andrew at Nick. So Andrew said another possible extension is to add to an evolving protoplanet envelope to self-consistently set the shock radius and add additional cooling luminosity. So thank you, Andrew. Okay, so we probably shift to our next speaker.
Yeah, I have a very quick question while changing. Yeah. So what stellar type range have you actually used it?
So there's
stellar property for this.
Yeah, I think we made some assumptions in like the gap opening treatment of just like, treat it as a solar mass type star.
Oh, okay. Yeah, so that's FGK star.
Yeah, but a lot of the actual fundamental like accretion
should be okay for
dependence doesn't really care about the star. It only cares about sort of what does the planet see as the local temperature. So obviously for hotter
But
stars,
it matters as the stellar luminosity matters for the radius of the planet. And then the influx of radiation, for instance, matter the vary between FGK stars and
Yeah.
M stars.
yeah. So it'll
It's just a factor.
it'll change like the temperature
Yeah,
that you put in.
fundamentally one.
But yeah, it won't change the actual physics, I guess. Yeah.
Let's thank